Assalamu alaikum. Today I will continue with with the third module, with the second module actually. This is vectors and matrices and operations. So it's basically telling more about the vectors and matrices. So I have Python and Julia in this one, languages in this one. So this is lesson one. This is the actual lesson one. Build a matrix class element-wise operations and distinguish element-wise multiplication from matrix multiplication. Explain when each applies. Implement a single dense neural network layer. Reload. This is the weight. Weight is a matrix multiplied by the input plus the bias using only the from scratch matrix class. Explain broadcasting rules how bias addition works in neural network frameworks. So this is designed for multi matrix multiplication. It is quite new, essentially. And then there's the weights are a matrix. The input is a vector. If you do not know what those operations do, this line is is magic. If you do know, it is the entire forward pass of a layer in three operations. Every image is a process is a matrix of pixel values. Every word embedding is a vector. Every layer of every neural network is a matrix transformation. You cannot build an AI system without being fluent in the matrix operations. The same way you cannot write code without understanding variables. Okay. A matrix multi what must be true about the dimensions? So the number of rows of the first should be equal to m should be equal to n. M should be equal to n, I think. Uh, the number of row m should be equal to p. Sorry, yes. No. The inner dimension n must match. So I know that m and n should no. The m and the number of rows of the second should match with the number of columns of the first. So n and n should be matched. Oh, right. N and n should match. My mistake. What is the identity matrix? With ones on the diagonal and zeros everywhere else, right? You try this check. So the inner ends must be equally right. Vectors order list of number. The vector is just an order list of number. This is a two-dimensional. This is a three-dimensional. Two-dimensional. This two-dimensional represent a plane, a 2D object, while a three-dimensional represent three-dimensional objects. Matrices are just grids of numbers. I have two rows here and three columns. Weight matrices transform input vector into output. A layer with 784 inputs and 128 outputs. It's in a neural network. This is important. Weight matrices transform into input vectors into outputs. A layer with 784 inputs and 128 outputs uses a 128 by 784 weight matrix. So the outputs come first. Outputs are the number of rows and the inputs are the number of columns. Okay. Uses a weight matrix, so I need to get this through my mind. So 128 rows and 786 84 columns. Matrix multiplication has a strict rule m cross n and multiply by n cross p is equal to mp. So these become equal to new matrix. This become the new matrix. So these are the weights, these are the inputs. So 128 by 1, that's the output. So the inner dimensions are valid in either case. Addition is element-wise, scalar is scale every element, learning rate gradients. This is the adding bias to the output. This is the learning rate gradients. Transform vector layer forward pass. Layer forward pass meaning I transform the vector from one layer to another. Transpose is the flip rows and columns. This is back propagation. I know a bit about transpose, but when it will come, I guess I will look more into it. Then there's a determinant single number summary checking invertibility. Okay, that I need to search about Wikipedia. Determinant, determinant, determinant. Okay. Uh, is a scale value square has many properties which take the fundamental study of square metrics and linear transformation represented by them. So this basically like this is okay. Now first properties, geometric meaning. That maps the basis vector to the column of A. This image is parallelogram, unit circle. So root value is the area of the parallelogram. The determinant basically gives the area and also Leibniz formula, Leibniz, and times and matrix, characterization and determinant, consequences. What was I actually searching for? I was searching for invertibility. Invertible. A square matrix is invertible if and only if its determinant has a multiplicative inverse. Invertible meaning is a square matrix that has an inverse, meaning it has an inverse. Or if its determinant has a multiplicative inverse. In the common case, when entries belong to a field, a matrix is invertible if and only if its determinant is non-zero. If the determinant is zero, then it is non-invertible, so I understand. So the transformation determinant helps me determine if an inverse exists or not. If it is non-zero, then the inverse exists, so it is invertible. Otherwise, it's not inverse. Undo a transformation basically. Solving linear system initialization. This is do nothing matrix. Initialization residual connections. One gets multiplied by this, so 1 multiplied by 5, 2 multiplied by 7. Element wise with matrix multiplication. So element wise is 1 multiplied by 5, 2 multiplied by 12. Okay. Made dot or products of rows and columns. So this is the dot product, meaning 1 multiplied by 5, 2 multiplied by 7. And then it gets added. So this is the dot product between the vectors. Broadcasting is basically since 1, 2, 3 is this is different from that, then this automatically gets added to that. Okay. When shapes seem wrong but the code runs. Vector or projection length of A, length of A, that is length of B, this is the angle. This is the projection. No, I already built this, but let's do it again. Projects AI from scratch and see the AI engineering, see the phases and code over here. Alright. Init add sub dot and then there's multiply. So multiply is with a scalar. I will add this on my own. Okay, what's happening? Um, so I just need to create a function mul self and scalar. So the scalar is going to be an integer, so I should put it in integer or float. Integer, float, double, whatever. It's just going to be a number. Is it a number type in Python? The most likely is number. So integer, int, float, integer or float. Now it's just going to return the self. It's just going to return a vector in which all of the x and y's, all of the components are multiplied by that amount. So basically, a scalar times x for x in components. That's it, I think. Self dot data. It's they have little data, but that's fine. Matrix class with core operations. So I have done this already, but let's see if I can add something else. Alright, I also need the vector magnitude, but I think I already did this. I mean, why did they put this here? This is more harder than these. This one. This should be first, I think. Then there's the add, then there's the subtract. Subtract each from each one of them. Scalar multiply. So I guess I'll do this now. Okay, so I got matrix multiply, and then there's the normal multiply. Where is it? So def add is going to be self, and the other one is going to be a matrix as well. Self other. So self and other is going to return a matrix in which um, the in which what's going to happen, right? So self dot components, self dot rows I j plus other dot rows I j for j in range, self dot shape. This is the row and this is the column for this is supposed to be the I. Self dot shape 1. Okay, I am going to delete this. I'm going to make a matrix mat1 is equal to this 1 0 0 0 1 0 1, and this is that. Then mat2. So this is just going to print mat1 plus mat2. And if I've done nothing wrong, then this should work. Hmm? Did it add or did it not add anything? I should add with I to produce 3, so it should be Python matrix with py. What's happening? It's not adding it for things. So I have done addition. I have to do scalar multiplication. Scalar multiplication. So it is with the vector, I think. So scalar multiplication of the vector. I have done that actually. Scalar. Have I done it? I have not done it, so let's do this. That is pretty simple. Scalar mult basically. Self and the scalar going to be int. Pretty sure I did it. Oh, I actually did it. It's up there. I did this. So this is done. Scalar. Where is it? All right. So that's done. Scalar multiplication is done with that. Now a matrix class with the core operations. Magnitude. Now I have to do matrix class. I have done the addition. I have to do the subtraction now. Subtraction is just copy paste this and just replace plus with minus sub. And that is it. Now what else is left? Now scalar multiply. Scalar multiply is so I simply have to do scalar multiply is just multiplying all the rows and columns with this, so with the value. So right here, scalar mult is self, and scalar it's going to be int or float, and oh, it's no curly brackets in Python. Delete that. And I am going to simply return a vector, a matrix in which every single component is multiplied by that value. So self.rows I j for I in range self.shape 0 and self.row again for j in range self.shape 1. So this is the number of rows, this is the number of columns, and it should work. if I have not done some stupid thing again. And that is done, this is done. Okay, so let me try it. So I'm going to multiply matrix 2 by some value. Mat2 dot scalar multi by 5. So it should give me 10 on the diagonal. Alright, I'm in phases. CDML fundamentals. And here Python matrix.py. It did not multiply it by any of that. Why? Am I doing something dumb again? Like, what am I doing wrong? What am I doing wrong? It will return to me a matrix in which, oh right, I'm not even multiplying with scale. What am I doing? So stupid. Okay, that's done now. Yes, now 10 on the diagonals. Yes, that's great. Now, what else do I need to do? Scalar multiply, element-wise multiply. Scalar multiply, that's done. Now, element-wise multiply. I think I have already done that. Element-wise multiply, this is right here. It multiplies by that value. What is element-wise multiply exactly? Oh, it's just multiplying. So 1 multiplied by 5 is 5. So element-wise multiply is different. So the def element-wise multiply itself, and the other is going to be a matrix type. And what is wrong here? Matrix is not defined. What do you mean? It is defined. It's defined right there. So how do I give the type of this self? I don't know, so I will ignore this. Return a matrix in which again self dot rows I j multiply by other dot I j for I in range of self dot rows self dot shape 0 and so, for j in range self dot shape 1. So this will do element wise multiply. So I simply have to create another matrix over here at 1, and it is going to multiply everything there by 3. So um, self dot element wise multiply mat 1. So this 6 matrix object is not alright. It should be like this. It's not component, it's rows. So I and j. Still not correct. Why? Oh no, I messed it up in the wrong place. Um, other dot rows. So 666, great. Now, if I add an element over here, like 4 and like 5 here, it should give me 20 in that spot. 20, great. It's working. It's giving me 20 in the correct spot, right? No, it's 3 to 6, 4, 5, 20. 20, it should give me 20 over. No, no, no. Oh, wait a minute. This is incorrect for some reason. So 3 multiplied 2 is 6. That's fine. Then 4 multiplied 5 is 20. 20 should be right over here. 3 2s are 6. That's working. That is also working. Then why is that not working? It's mat 2 multiplied by mat 1. 5 to 20, 20 should be here and 6 should be there if I'm not mistaken. Why is that not correct? 5 to 20, 0, 0, and 3 to the 6. What is wrong? What is wrong? What is wrong? Wait a minute, that So let me visualize this. So something like this. So this becomes 2, 4, 0, and 0, 2, 0. And I could just yank the, what am I doing? So 0, 0, and 2. How do I put it over there? So again, it's 3, 5, and 0 multiplied by 0, 2, 0. No, 0, 3, 0. And multiplied by 0, 0, and 3. Yes, I should see 20 on the top row. There is something wrong over here. So I am doing something wrong here. Other self dot shape 1. And there's something wrong here, like I is 0. It is 0 for the first value. Wait a minute. No, that is not correct. This should be J inside over here because no. This should not. No, this should be J. So this is iterating over the columns, and this is iterating over the rows one by one. So in this case, yes, that's correct. So this was also wrong. I was doing this wrong. So J and this I, and that should also work. So scalar multiply should also work. No, change till this. Scalar mults by 5. So it should multiply the second one by 5. So this gives me the 10, 20, 0, and 10, 10. That's great. It's working. Fine. Broadcasting. So when you add a bias vector to a matrix output, the shape do not match. Broadcasting stretches the smaller array to fit the bigger one. So all I have to do is take a matrix, take another matrix, add them. If the second matrix does not have equal dimensions, then I need to stretch it. Broadcasting stretches the smaller array to fit. So def broadcast. This is self and other. So basically, if one of the matrix shapes is not equal to the other, stretch it, stretch it, stretch it. So basically, I need to increase the size of the other one. I got one matrix and I need to increase the size of the other one somehow. So what will I do? I will take the smaller one and just fill its stuff so that I will just fill in the values there, but there could be an easier way. There must be an easier way. Add. So this add is the two vectors together. I mean, broadcasting should be done by the that operator anyway. So what should I do? Um, so go through the bigger matrix, just add the elements from the second matrix to the first. So for I in range self dot shape 1, shape 0. This goes for j in range self dot shape 1. This goes through the second one. I need to add them together one by one. So first of all, I should just write that. So self dot shape rows I and j is plus self dot rows I am It's something like this. So this is the this will simply add the two, so it doesn't do anything different right now. So what should I do? So this one loops through the I guess I would need three loops maybe. One loop goes through this one and the other goes through this one. Is that correct? Is that correct or not? Hmm. I could do this in another way, like how new matrix dot append a plus b for ab in zip, the self dot rows I and other dot rows I. So it adds them together and appends that. So we uh, inside this adds around no adds surrounding. It was somewhat I forgot. Well, whatever. So this will give me just a matrix. This will just add the two matrix. So let me just replace this with this so it's simpler. Print mat2 dot broadcast mat1 555. So that is working. Now I need to. How do I go about doing this? Broadcasting stretches the vector across rows, smaller array to fit. But if the first one is smaller, now let me first solve this one. I'm going to each of them, then I simply add them together. If other dot length of other, no, if the other dot shape 1 is less than self dot shape 1, meaning no, the other rows are less than the current one rows, then other dot rows dot append for I in range self dot shape 0 self dot shape 0, meaning the I need to match the two shapes. So other dot rows dot append the other dot row I. This will keep on appending the row until it matches the shape. Oh, I think I should do a for while loop here. What am I doing? This is while other dot shape not equal to self dot shape 0. I am going to keep on appending the row and I am going to keep on appending the row. So I don't have I here, so um, there must be another way, like I dot 0. I just get the first one, I keep on adding it, or something like that. So let me just erase these two, and this as well, I suppose. And if the other dot shape is greater than that, and other dot shape is not equal to the, meaning the other rows is greater than the first row, then in that case I do self dot append self dot row, if that makes sense. Python other dot row is right. It's stuck in an infinite loop. Alright, I also need to increase the shape. What am I doing? Other dot shape is going to be plus 0 plus equal 1, since I'm increasing the row, and in this one going to self dot shape plus 1. What? It is out of range? What does that mean? So if the other shape rows are less than the current, append more rows to the other. Other rows are less than the self rows, then while it is less than that, I append more rows and I increase the shape. Tuple does not support an darn. Well, I'm gonna break this rule, okay? Its shape changes, yeah. So three. Yes, it's working. So let me see something like this would work. So this is going to add this 5 2 2 and 3 4 2 and 3 2 4. Yes, this is working. Let me do the opposite since addition is commutative. 5 2 2 and 0 4 3 4 2 and 3 2 4. This is working as well. Let me try the matrix that they have given. 4 5 and 6, 1 2 and 3. And chin is at this, so this is going to be 4, 10, 20, 30. And this is the result. 11, 22, 30, and 14, 25, and 36. Now let me see their implementation. How did they implement this? Inverse, add, element-wise, transpose, inverse of 2 by 2, identity. Did they not implement this? I think my broadcasting thing is okay. How do I confirm? I mean, it's working fine. Passes the test. I want to check if it's correct. How do I go about doing that? The only way is I could make an AI check it. I could make an AI check this. Hmm. Actually, since they are using tuples, then I think it would be better if I use a tuple here as well, because if it's a if the what was I going to say? If it changes the original matrix, then that's a problem. It's changing something that's outside the function. So that is a problem. So I would make another new new other, but that's going to cause a problem as well. And that is a simple solution. If this is the case, does Python automatically create a copy of class when passed into a function? No, it does not. So if that's the case, then if I try to print mat2 after it, its entire shape would be changed, wouldn't it? Oh, that's bad. So that's the problem. That's a problem. The problem is that it's changing something that's outside the function. That is not correct. It should not do that at all. Then what should I do? What should I do? What should I do? I could create a assignment with this how to actually copy an object. Copy dot deep copy. Import copy dot deep copy. So import copy. But this is an they have not implemented this in is around this with this. They have not implemented this in their thing. Have they? Is independent Graham Schmidt. This is the addition and where is the broadcast? I guess I could check it on broadcasting a matrix algorithm. But what is the actual algorithm for it? Like um how does the broadcasting work under the hood? Data in RAM shift to get column. No, that is good and all. I want to just check my broadcast function then. Is my broadcasting function good? I know it's going to say that it's going to change the outside value. Logical issue place side modifications, yeah. So it was not as simple as that. Well, it's not as simple as that, I guess. But I'll delete this. I'll do this later, inshallah, if I find the desired tool. I thought that would be easy, just stretch the matrix, but no. Alright, so I was at implementing the broadcast method, but I skipped it because it was just too much for some reason. Anyway, the transpose were done in the matrix. The transpose was done, I believe. Transpose is done. Now I need to do the determinant self. Determinant is a bit tough because some of them are negative as well, some of them are positive. That's the thing. The 0, 0 is positive, 0, 1 is negative. It's positive, negative, positive, negative. There is sure to be a another formula for the determinant. Like I know how to do it on paper. I don't know how to write the algorithm for it. Actually, I also tried to do OpenCV. You know, I was talking about building a whiteboard, but for some reason, the OpenCV documentation is absolutely horrendous. Like it's very bad. Like there was a function I wanted to search the function here. I could not even get what it. I could not even get the function. It was just bad. No, I suppose I could code this in C++, but I don't have the desire to run. Maybe I will do this later then. Now I will determinant. That spelling is wrong, but whatever. Determinant. So I know how to calculate the determinant. This is basically there's the Saro's rule, meaning I multiply this, then I multiply this, then I multiply this. That's that. So how do I make the thing wrap around essentially? So I know that AEI, that is simple. This is just 0, 0. This is 1, 1. This is 2, 2. Simple enough. And the sorrows will also work on this, then this. It will also work on that. Now I want to implement the sorrows rule. How do I end up going? So this is 0, 1. This is 1, 2. And this is 1, 2. And this is 2, 1. 1, 2. And it cannot be 3. So it wraps around to the next one, which is 3, which is 2. 1, 2, 1, 2, then I do 1, 2. So this is 1, 1, this is 1, 1, 1. So the row is increasing and the column number is increasing. This is 0, 1, this is 1, 2, and this is 2, 1. No, 2, 1, it should not go to 2, 1. It should go one step back to 2, 0. I suppose it's the remainder. I could do the modulus on that. So this becomes 0, 1. This becomes 1, 2. And since the I is going to exceed since the column number is going to exceed the matrix columns, I just take the modulus of that. I suppose, yes. So how do I go about doing this? Okay, that's I will do this, and then this. So this becomes 3, 3, 3. Then this becomes 0, 1, 2, and 2, 2, 2, 2, 2. Then I increase it by 1. I take the modulo. This becomes 0, 0. That is not correct. It should become, I should increase it by 1. That is difficult. Like, how would I write this programmatically? Well, I could simply write the formula. Like, I could simply write it. That's not the problem. I know this R's rule, but how would I actually calculate it? Like, how do I implement it? How do I implement it? I don't get it. I don't get it. Is there any other way? The thing is, I can do this on my own, but it will just take a long time. And I know that it is a recursive formula because if it was a four-dimensional matrix, 4 by 4, then I would shrink the matrix depending on that. And yeah. So how do I go about doing this? This is that. Then for second one is A to B, B minus C. How do I go about doing this? I just don't understand. But I guess I'll look at the solution of it. Hmm. So how have they done? If the shape is 1, 1, if the shape is 2, 2, and if the determinant range self-dot columns, minor dot determinant. So they are calculating the minor. So it depends on the column. So plus, minus, plus, minus. Now this does not make sense. So the first column is obviously the positive, then the second is negative, then the third. But if I move down, then it changes, doesn't it? Because positive, the one below would be negative. So I don't understand. I mean, I can do the 2 by 2 and 3 by 3 matrix. That's not the problem. If self dot um, shape is equal to 1, 1 double equal actually. Return the and the self dot rows 0. If self dot shape equal to 2, 2. Does that actually work in Python? Like, can I make the two lists? Self dot row 0, self dot row 1 and 0. Oops. Okay, this is good enough. Now, does that actually work in Python? Like list 1 is equal to 1, 2, and list 2 is equal to 1, 2. Then list 1 equal list 2. True. So if I make a list 3 equal to 1, something like this, then what does it do? List 1 equal to list 3. Wow, so it works. That works great. I guess I should test this out. I could do the determinant of any matrix, like determinant of any matrix mat is equal to matrix. I will make a 2 by 2 matrix, 1, 2, 1, and 2. So the determinant of this would be 0 because both of them lie in the same plane, I suppose. Because both of them are in the are collinear. They won't have an area, I guess. I think. So print mat the determinant and Python matrix. TDML fundamentals Python matrix.py. All right. It's supposed to be like this. It does not take into arguments. Determinant is 0 now. If I increase this to like 0 or 1, in this case there will be a determinant. It is 1. Um, 1. Yes, it is 1. That is fine. Now I need to determine the um, the minor of the matrix. For I in range, I'm going to make determinant equal to 0. I'm going to return the determinant, the shape 0. For the number of rows, now also for j in range, the shape 1. I need to determine the determinant of the minor. So I ignore the first row and the column. I will ignore the first row, the row that the I is on. So I will only take that element and I will take the determinant of the remaining. How do I go about doing this? How do I get the first element? How do I get the elements that I am working on? I simply do mm, self-dot rows I and j. So this is suppose this is a 3D matrix. Like let me make one. Mat 2, 3, 3. This. So it's going through here. All I need to do, this is positive. And I need to get the determinant of this remaining thing. Then it will move on to this. Then I need to take the determinant of remaining this. And then I need to take the determinant of the remaining this. Okay. But currently the problem is it will go 0, 0, then 0, 1, then 0, 2. Thing is, it should stop. That's it. It should not move forward. Meaning, once it goes through the one of the rows, once it's done with one of the rows, it should break. So that's it. Now, what do I do? How do I get the minor of that? How do I get the minor? So, suppose I'm at 0, 0, I need to determine the minor of um, 1, 1. I need to determine the. I will ignore the first row, meaning since I am at 1, I am at 0, this is 0, 0, so I will ignore the 0 column and the 0. Um, I will ignore the 0 column and the 0 row. Right. I will ignore the 0 column and the 0 row. If I is not equal to j and I is not equal to j, meaning I ignore those, then I get the determinant of the leftover. How do I get the determinant of the leftover? Think, think, think. How do I get the determinant of the leftover? Well, how do I do this? How do I do this? So this is going to ignore this column and this row. Now I need 1, 3. I need to multiply 1, 3 minus 3, 1. How do I do that? I need to multiply 1, 3 and 3, 1. It's just a 2D matrix. Well, perhaps I could do it recursively. I could throw in this matrix that I have currently and throw it in. Actually, let me try that. Maybe that will work. I could do this recursively, perhaps. So I is not equal to the j. Then what I need to do is I need to simply just take the current matrix, copy the rest of the stuff. Forget about breaking. I need to copy the current matrix. The current matrix is equal to, where should I copy the matrix? That is not going to work. I need to copy it outside, I think. Matrix mat copy equal to none. then it's going to be a row equal to this, and then row dot append. Then I am going to append the self dot rows I and j. I'm going to append the I and I'm going to append the j. Is that correct? Now this is going to append to the row, and at end of the loop I append to the match copy row. So I get the copy of the matrix each time. Then I need to determinant of the. Okay, so the problem is it's the self dot determinant. That is not correct. Um, so the thing is, if I input, this is not good. Um, this is doing the self dot determinant. I want it to calculate, make it calculate the determinant of the other matrix. So, some thinking of doing a recursive process, but I just can't seem to get it. I did what I could. So the algorithm goes through the columns, shape of one. It goes to the columns, and then it does minor is equal to the matrix. Um, Matrix. It creates another matrix. I in range self. It goes from 1 to self dot shape the number of rows. But this formula wouldn't be good for a four-dimensional matrix. I think that the self dot data it goes through the first row, and for k in range self dot shape if k not equal to j. So that is it. And there is something wrong here. What's wrong? The bracket wasn't closed. Which bracket? This is closed. This is closed. Then this. This is also closed. Then what is wrong? Some bracket wasn't closed. What's wrong here? Okay, I guess I'll write again. For j, oops. For j in range, solve shape 1. I in range, I in range. No, I guess I should do it. This matrix. Hello data. Self dot rows. I k for k in range. Self dot shape dot 0 dot I, meaning the columns if they not equal to j, and then for I in range 1 to self dot shape 0. So this, the outside goes through the rows and the inside goes through the columns one by one. But what I don't understand is how would this work on the on a 4 by 4 matrix? So the next one I'm gonna try to do myself. I'll try. So the determinant plus equals, I add to the determinant the minus 1 multi raised to the power j. Oh, right. Oh, that was the formula. Matrix determinant. So the minor dependent, I just want to see the formula here. Where is the actual formula? So this is I plus j in this case. So this is I plus j, but this is not going through that. So this is doing something else entirely. Well, whatever. So it is minor times the self dot rows 0 and j, meaning each of the column multiplied by the minor dot determinant. And in the end, it keeps on adding to that and then it returns it. It should be raised to the power of I minus j, but I don't understand this thing I'm sad about. I don't understand how would I do this myself without looking at the solutions. I want to become good enough that I am able to do this on my own without needing to look up at the solution over and over again or asking an AI. I want to become competent at this. I couldn't have figured this out. I mean, I guess I could have, but it would have taken me a long time. And it's not possible in this day and age to have a lot of time. Okay, so I understand how this works now. This is going through the column, and this is going through the rows one by one. This is again going through the column. This is again going through the column. So I am ignoring that, then it is I can okay, and that. Well, it's just making the minor. It's making the minor. Then what's it doing? What is it doing then? Why is it one? Why does it start from one? Why does it not start from previous? So I in range self dot shape 0. So I guess it is removing a row one by one. But couldn't I also do -1 to get the same feature? This is referred to as the cofactor, and I want to code this on my own. Now, I understand I want to code this on my own using the my own method for this, I guess. So the determinant is the same equal to 0. Then I simply do pass through the rows and the columns one by one. I pass through the columns. Should I put rows first or column first? Since I'm going through a column one by one, meaning in the determinant, you can go like this or like this. I'm going like this, like they have done in the solution. Shape 1. Hmm. Hmm. Alright, continuing. If the row is not equal to the column, I go through the column again. I basically made three loops because one is going to go through the outer and one is going to go through the inner one. So in a sense, now if the row is not equal to the column, I push to the minor. First of all, I need to get the value, the cofactor as well. I need to get the cofactor every single time. So cofactor is equal to the um, how do I get the cofactor now? It's I plus j. So do every time I reassign the cofactor. Okay, cofactor every time is none, and the uh, what is this one called? This right here. This is called cofactor recursive known as the minus is determined. That is known as cofactor when equally called this is called Laplace expansion. So multiplier is equal to self dot rows 0 and j. This gives me the multiplier. Now every single time I am going to go through the row, that is a problem. Like how do I get that? Right, I just have to do, oh, it's going to be plus minus plus. So the first one is, oh, right. So what they did was correct. -1 raised to the power j. So this becomes um, plus, then minus, then plus again because it's a square. So that's that. Then I simply add the minor to the row. So I add minor row dot append the minor row dot append that First I'm going to get the minor as well. I need to minor is equal to this. Then minor dot row dot append. I'm going to append to it self dot rows a row and call. I'm going to append the row and the column as long as it is not those are not equal to each other. Right, is that correct? Am I missing something? I hope not. Okay, each time it goes through that. Okay, then I append to that minor dot row, and at the end of that minor dot append minor row, and in the end I turn it into a matrix. Minor matrix is equal to matrix of the minor. Then I get the determinant. The that of the minor. What's wrong? Minor is, oh, it's big M. I am stupid. Right here, so it's supposed to be like this, and then like this, minor. Okay, so determinant plus equal the cofactor multiplied by the multiplier, and then the multiplied by the minor dot determine the minor matrix dot determinant, and in the end I'm going to return the determinant. That's it. I hope this is correct. So first let me do the minor of a uh, let me do the determinant of a 3 by 3 matrix whose determinant is just going to be 0. This is a unit matrix, so its determinant is 1, right? So to the determinant, let me do this, and I got an error. It's out of range. Why? Why is it out of range? Which is out of range? Um, what thing is out of range? I don't get it. Okay, I guess I'll do the debugging. I have not used the debugger at all that much, but Python debug Python file. Okay, step over. Okay, so this is how it's working. I guess I should use the debugger a bit more. So where does it actually crash? So row is 2, the row is 2, and the column is 1. This is the second row. The second row is 0, 1, 2, and then, oh, this is confusing as well. Hmm. So it gives an error 2, 1. So the row is going to be 2, 0, 1, 2, and then 1. So what is the problem? So 0, 1, 2, and then 1. It gives an error here. Why? So it's working fine. It's just not working here. Why is that? Why is that like row 2 and column 1? So 2 and 1. It should give you a value, but it does not. That makes no sense. Hmm. What's wrong? So this is the problem. This module math to the determiner. That is not correct. What have they done differently here? So it goes to the column. It goes through the shape on the column again. Row and column. There is a flaw with my implementation. What is the flaw here? There's a flaw with my all zeros. There should at least be a 1. I don't understand. It's going through the column one by one. What I need to do is I need to ignore the current. I need to ignore the current row and the current column. I need to ignore the column, and I don't need to ignore the row. So I don't get it. I will start at the row and go to the next column. Make it more English. No, actually, I'm going to go through the next row and I'm going to match the columns. What is wrong though? I guess the minor is not being calculated correctly. But first it is 1 zeros at the 1 0 0. I think this should be right away. What is happening? This is kind of more but it is giving me 0 1s. And this is giving me the minor. But there's a three-dimensional minor that is not good. That is wrong. Guess I'll use AI to check. Not even one of them has a 1. Not even one of them has a. So K and self-dot should 1. That is the column under that. K not equal to J. So K not equal to DJ, which is the row not equal to DJ. Okay, that is working. That is seems to be working. Not really. Hmm. I'll check this with the AI because I just don't know. Keep the current column entire. That is it. That was the entire problem. Malformed minor matrices. So it's supposed to just skip the entire column. So this already skips the row. Okay, I understand. So it's only one thing was wrong. Well, that's okay, I guess. Let's continue now. There is the transpose was done. I need to do the determinant. Inverse of 2 by 2. Is the inverse of 3 by 3 by 3 is not. It's not a 2 by 2 matrix. No, otherwise I'll need to do the inverse. The inverse is okay, so in the inverse of a 2 by 2 matrix. In the inverse of a 2 by 2 matrix, inverse mat is equal to matrix 1 2 2 1. So it's I flip these and I turn these into minus. So first I need to get the determinant. Determinant deter is equal to the self dot determinant. Determinant. I get the determinant of myself, then I switch the matrix. So I need to swap these. I need to. So let's say 1 and 3. I need to swap these. It's going to become 3 1, so 0 0 0. I need to swap these two. So self dot rows 0 0 as 1 1. Self dot rows 1 1. Self dot rows 0 0. So this swaps them. I need to make a copy of the original one as well. So I I and range self dot rows self dot shape 1 should be self dot shape 0. No, this is 0. This is going to be 1. What's wrong now? That was not closed. What do you mean? Copy is equal to matrix for I in range self dot shape dot 0. This goes through the rows and this goes self dot rows 0 I j in range self dot shape 1. Okay, this gives me the copy of the matrix. Return mat copy. Return mat copy. So print method inverse to it. Okay, great. Now I need to inverse this 0 0 is equal to copy 1 1 is equal to copy for 0 this swap to, and I need to change the sign of the others too, so mat copy 0 equal to multiply by minus 1, mat copy 1 0 multiply by, then I am going to divide each of those by the determinant row and range. Then I'm going to set a mat copy dot row dot call is equal to mat copy row call divided by the determinant. Alright, swap diagonal change sign of other diagonal. I want to see some examples, so I should make a 1 2 2 minus. Oh, right, I get this 0.2 right and 2.4 minus 0.2. Great, it's working. That's it for today, at least for now. Thanks for watching. Alright, we will be continuing with this. I was right here, the inverse of 2 by 2 matrix. Now I need to confirm, I need to check if it's an identity matrix. So I'm going to go into code again. So identity matrix, that is pretty easy. All I need to do is check if def identity is identity matrix self. Will take the self and it will return I need to check all of them. Return true for I in range. Self dot shape 0. The J in range self dot shape 1. The spelling is on shape and shape. If I not even if self dot actually I already need this one row self dot do only square matrices have um identity matrix. Yeah. Must always be a square, so that is easy. Self dot rows I meaning 0 0 then 1 1 then 2 2 not equal to 1, return false, otherwise return true. So all I have to do is mat dot is identity matrix, and that's it. Right, cd ml fundamentals and python matrix.py, and this is not an identity. Let's make another matrix. Mat 2 and 0 0 1. This should be mat 2. True, that is good. That's done. That is the transpose. Okay, now it's connecting to neural networks. So neural network dot example dot py, and inputs equal to a matrix. It is a matrix of two-dimensional vectors 0.5, 0.8, and 0.2. So it is just a vector. This is just a vector in the end. I know it. So from matrix import matrix. Really. So those are the vectors. Then I have the weights matrix, and I am going to make a random uniform. The range depending on round. This means variance of random variable a plus b divided by 2 and b a raised to the power 2. There's the variance. Uniform. This produces a uniform value between 1 and 1, minus 1 and 1, and for dash in range 3, and for dash in range 2. So this creates a 3 by 2 matrix, a 2 by 3 matrix. Now I have a bias which is as a matrix 0. 2 by 2 0.1 is just a bias, so 0.1. So ReLU, the ReLU matrix, return a matrix, a max 0 val for val in row, for row in m dot rows. M dot rows is just going through the each row and it's getting the value, and it is getting the maximum of 0 or val. What does this stand for? What does ReLU stand for in neural networks? Rectified linear is artificial in an activation that decides whether it should fire or stay. An rectified linear unit. It outputs input directly if the number is positive. It outputs the input directly if the number is positive. It outputs 0 if the input is negative or 0. So if the input is positive, it just outputs true. If it's negative, it remains false. It is equal to max of 0 or x. If x is an input to a neural, to half a rectification is one of the most powerful activation functions. Computer vision speech recognition. This um, advantages pointage can be chosen to be 0 or 1. So piecewise linear variance. X is greater than 0, meaning it's just x. And if it's less than 1, it is multiplied by some constant. If it's greater than 0, it's activated. The derivative, it's the units and I have omega, the vanishing gradient. The gradient is defined by the parameter a. Okay, where do I get the definition of a? This is x positive or max of 0 or x. So it chooses 0 or that, meaning if it's bigger than 0, it activates, otherwise it does not activate. That's it. The input is negative or 0. 0 means it doesn't activate, or if it's positive, it activates. Now linearity formula, leaky, then there's sigmoid, smooth output, good probabilities in this soft max. Okay, that's good. So for each value in the row, it becomes 0 or 1 essentially. Pre-activation is equal to weights dot matmul by inputs. Matrix multiplied by the input. I haven't weights just multiplied by the inputs. What are the inputs? The weights multiplied by the inputs. I don't know why would that won't work right, because this is I'm going to make 3 columns, and it's going to make 3 columns and 2 rows. Well, this is 3 columns and 1 row, 1 by 3. Yeah, this is 1 by 3, right? But couldn't it also be written like this? So this is 3 by 1. Well, technically yes, but in computers it is just row-wise. Well, I think this will work. Plus the bias. It's going to add them together. So this is going to make so the first was 1 by 3 and the second one is 2 by 3. So it is going to make 2 by 1. 2 by 1, then 2 by 1, then that gets added to this, which is also 1 by 2, and that makes a new matrix. Wait a minute, so that is 3 by 3, that is 1 by 3, so this 3 by 1, so that makes a 3 by 1 matrix. 3 by 1 matrix, so this is going to make, if I multiply these two, this is going to make 1 by 3 multiplied by 3 multiplied by 2 by 3. This is going to be 1 by 3 matrix. Now 1 by 2 matrix. I'm confused about that, but whatever. Print pre-activation. This is going to even work, or am I doing something wrong? You unexpected indent. Alright. Inside this and add surrounding this matrix time matrix that is there. I'm pretty sure. What is this? Now, what do you mean there is an operand here for that matrix mold? It's right here. It's right here. What's wrong with this? I don't get it. All right, it is this mat. Okay, this is going to mat multiply and then add the bias to it. Then also I have the output. Our output is equal to relay matrix pre-activation. So this is the essentially the neural network. It takes the weights, it takes the inputs. Input times the weights. Weights time the input plus the bias, a certain amount of bias is added. Now if it's negative, it is turned off, and if it's positive, it's turned on. Printf input shape, inputs dot shape, weight, weights, shape. Oh, it's this, no, that is the shape. So what is the ruler doing? Is max value for that, for val in rule. I haven't written this correctly. Evidently, does this matrix multiplication. It's at the bias value rectify linear unit. So this basically makes it so if it's less than 0, it is not activated. If it's greater than 0, it's activated. That's the gist of it. NumPy does everything in the fewer lines. So NumPy example, NumPy neural network example.py. Import NumPy as np, then a is equal to np dollar. Could just copy this one, and then this is the inverse linear algebra, determinant. A dot t is the transpose determinant inverse. This is the identity I of 2. So now I have inputs is equal to np dot random rand n 3 by 1. It's a 3 by 1 dimensional matrix. The second one is weights. Weights is equal to np dot random rand n, the 2 by 3 matrix. 2 by 3, I think. And bias is equal to the np dot array 0.1 and 0.1. Output is equal to the np dot maximum. This is the result. Let's check this, and it's Python NumPy neural network example. There's a bias. What is wrong with this? So the output is 0, and no, I guess this is just how it is. So if it's greater than 0, it remains, otherwise it's just 0. So this was greater than 0, it remains. And the other was less than 0, it was, what was it? Weights dot shape, input dot shape. Why is it 2 by 1, 2 by 3, and 2 by 1? This is uh, print 2 by 1, so it is 2 by 1, so this is 2 rows and 1 column. I was confused first, but now I understand. There's 2 rows and 1 column actually. Okay, I understand. So it's multiplying the weights by the inputs with multiplication, adding the bias, and if the total result is greater than 0, it is activated, otherwise it remains 0. Verify the inverse. Okay, so the inverse I made, I want to check it. So let's do this. So A is equal to matrix. Matrix. I'm going to make a matrix like this. 2, 3. Right, it's a 2 by 2 because I'm not good enough to make the 4x4. That requires the calculating the minor matrix of every single one of them, getting the determinant and putting it there for 3x3. That is a lot of work. Actually, I might implement that later in spare time, maybe. So I have to print the mat inverse A dot inverse of 2 by 2. It should return a, this should return a 1 by 1 or something. What is wrong here? All right. Yes, identity matrix. Try what happens when the determinant is 0. So determinant is 0. It's going to be something like this. Determinant is 0, so in this case it's going to throw an error division by 0. That is not correct. So I should find the determinant if deter equal to 0, then return the matrix is not um, singular. The singular matrix have determinant of 0. Yes, singular is singular. It doesn't have a inverse. No. What is wrong? What did I do wrong? What have I done? No, I wanted to return. What is this doing? This is going to the line number 51. 0, 0 times 1, 1 minus, um, so 0, 1 times 1, 0. So this should work. I don't get why this is not working. So it is not multiplying it. So A times A dot inverse. Oh, this is returning. So I guess I should just throw an error. Return 0, if that's going to work. So the inverse doesn't exist. How do I guess I could just throw an error. Throw does it is just throw return a matrix that is just so for a 2 by 2 should just be 0, 0. Yes, 0, 0, that's it. Implement 3 by 3 inverse, extend the matrix compute, test it against, build two-layer neural network using only your matrix class, no numpy. Create a two-layer neural network. Has three inputs, initialize, run a forward pass, verify all shapes are connect. Okay, this is an interesting project for later, but for today, this is enough. Thank you so much for watching if you joined me till the end. And thank you. Allah Hafiz. I will see you later. Bye bye.